Hello everyone, again Pranav here. Today I am going to explain hydrogenerator part 6. All other links of the previous parts are given under the description box. Manufacturing process of stator winding bar. Based on different capacity of hydrogenators as depend upon the water head available at site, the stator bar has to be designed accordingly. The hydrogenerator with salient pole rotor is of air-cooled type of lesser length in comparison to the bigger diameter. Stator winding, in which electromotive force is induced and supplies the load, is placed in the slots of stator core. As the large generator intends to have high power density, so the circulating currents in the armature winding also would have become large, and hence the loss must be high, causing an overheating. In order to suppress losses caused by eddy currents and circulating currents, the stator coils of these generators are normally comprised of multiple copper strands of rectangular cross-section insulated separately. Stator coil is made up of number of strips instead of single solid piece of copper to reduce the skin effect. Bundle of copper strips, when consolidated in a single part, is termed as stator bar. Because of comprising with fine conductor division, eddy current losses would have become reduced compared to a massive copper bar. Copper material is much more suitable in manufacturing stator bar as because 1. It has high electrical conductivity with excellent mechanical properties. Number 2, immunity from oxidation and corrosion. Number 3, it's highly malleable and ductile metal. Now, Roebel Bar Transposition. Individually insulated or non-insulated copper strands are required as the basic material for manufacturing the bar. The insulation component of the strand may be of iron or fiberglass of F-grade type or more based on the design temperature range of 155 degree centigrade to 240 degree centigrade. The pre-insulated copper strands are then cut to form bars of required slot length. The manufacture of winding bar from these insulated strands is specially configured as Roebel bar. Roebel bar was invented in 1912 by Ludwig Roebel, 1878 to 1934. A Roebel bar is a winding bar made of these strands of improving the efficiency and performance of large electrical machines. Now let's see the strands profile for the Roebel transposition, that is change, reversing of level 1 to level 2 and perform bars after pressing. However, technological sophistication in manufacturing process of Roebel bars with conductor strips for stator windings relates to an improved Roebel bar transposed bar for stator windings, which eliminates tearing of transposition insulation and interstrip short circuit. Roebel transposition is a process for making stator bars in which the individual conductors that make up the bar are twisted together, which is called plated, in such a way that each individual conductor occupies every position within the bar at least once. The transposition virtually eliminates circulating current losses in the coil by ensuring that each strand occupies the same height position for the same distance as every other strand. Advanced phase of Roebel transpositions represent significant improvement over previous methods of transposition designed to reduce circulating current losses. The transposition of the insulated strips can be in multiple of 180-degree, which means traverse of individual strip from top of the bar to the bottom. This arrangement is similar to bending, twisting, plating of bunch of strands. Transposition of 360-degree means transverse of each strip of copper from top to bottom and back to top in the given active oblique straight length of the bar. Major aspects fulfilled by using Roebel transposition process in designing stator winding are as follows. A. Lesser winding losses due to transposition of strips with respect to the flux generating surface of the generator rotor. B. Skin effect, that is, tendency of current to flow in the outer layers of conductors. Losses of the conductors are less. Thus, the efficiency of the machine is higher. Concept of transposition of strips in an interwave pattern allows to equalize the flux linkage among all the strips irrespective of their differential radial distance from flux generating plane, that is, the rotor in case of synchronous generator. This results in equal induced voltage generation among all the strips of the bar and avoid interstrip circulating short-circuiting current. In a Roebel bar of 360-degree transposition, all the strips travel from top to bottom and then up to the original top level in the given active state part of the generator. Depending upon the requirement, the transposition may be repeated or may be continuous in the active length of the machine. The winding is manufactured or assembled with individually manufactured bars laid in stator core as per the winding pattern. For single turn bars, the 360-degree Roebel transposition in the slot portion is most common, while a more efficient 540-degree Roebel transposition can be accommodated for the longer core length. As high as 900-degree Roebel transpositions can be incorporated by adding transpositions in the end turns. Roebel bars have become more acceptable than the less expensive multi-turn coils as because 1. Eliminate the possibility of interturn insulation failure, easier to remove from slot position. Number 3, the Roebel bar design of stator winding fulfills The lesser winding losses due to transposition of strips with respect to the flux generating surface of the generator rotor. Number 4, losses of the conductors due to skin effect are less, that is, tendency of current to flow in the outer layers of the conductor. Thus, the efficiency of the machine is higher. Manufacturing process of Roebel bar. Depending on the design of the bar, the number of insulated copper strands as needed are arranged in a horizontal tapering manner and are clamped to avoid any further separation. These strands are pressed by the hydraulic press to create the down and upper steps or bends on the strands for the Roebel transposition. Two sets of strands are arranged in transposition with one set on top of the other and other tied together. A bonding or filler epoxy putty tape is then wound around the arranged strands on the sides along their length. This epoxy material has become hardened under room temperature, and this would used as a bonding or adhesive agent and filler for the strands. The strands are pressed to cure the epoxy to make a performed Roebel bar. At this point, each strand is tested for continuity and short circuit tests between the strands are also done. When the bar withstands all these tests, it is then taken for bending into a lap or web bar in a bending robot machine. The bending robot machine should be made so precise to meet all sorts of bending radius criteria according to the design specification. After bending, measurements are made to verify the required ready or radius are achieved. The bar is then braced at the ends and a bracing tab also attached to facilitate joining of the bars to form a coil in the winding process. The mica tape ground wall insulation is wrapped around the bar. This is followed by the anti-corona tape, that is conductive tape, which is wound along the bar length only until where the stator core ends. Another semiconducting tape material is used for corona protection on the bar overhang portion. The composition of the tape material chosen for the corona protection should be compatible with the ground wall insulation. The bar is then ready to place for vacuum pressure impregnation, that is VPI, where any voids in the insulation and bar are sealed. The advantages of VPI include low tan delta values, longer insulation life, and better heat dissipation. After curing from the VPI process, the bar is ready for stator assembly. During the winding assembly, round packing is used to ensure optimal fit of the bar into the slot. Round packing is when a double layer tape enclosed with a silicon compound is wrapped around the bar only to the length of the core. The bar is inserted into the slot and allowed 5 to 10 hours for hardening. It's a automated high precision machine for manufacturing transposed Roebel bars for generators. And the arranged strands where the filler resin epoxy is applied, perform bars after pressing, finish Roebel bar, bend performed bar with corona protection is shown in the picture. A typical Roebel transposed bar consists of A. Double glass covered insulated copper strips in two halves. B. Half insulation with thermoset epoxy glass fleece sheet. C. Half insulation extension with fine mica cloth. D. Transposition insulation Nomex glass fleece sheet. Transposition surface filler with foam micanite putty. F. Main ground wall insulation with resin pour mica tape and outer corona protection tape. Bars are thermally cured in a mold at 155 to 165 degrees centigrade for a stipulated time period. Polyester film is then hot fused onto the individual conductor strips and with glass yarn or fiber as the final layer of strip insulation. Due to high abrasive resistance of the polyester film in the conductor, which results to provide electrically short-circuit free stator bars. The additional interhalf insulation avoids electrical short circuit between two halves of the conductor strips stacked one over the other and between two conductors at Roebel crossover during transposition. With the imposed insulation arrangement, it is possible to have a lower value of ratio between transposition pitch to copper strip width, which allows addition of more number of copper strips in a bar cross section, resulting in lower winding losses and has to minimize the skin effect because tendency to current flow to the outer layers of the conductor. Roebel transposition is a process for making stator bars in which the individual conductors that make up the bar are twisted together such that each individual conductor occupies every position within the bar at least once. The transposition virtually eliminates circulating current losses in the coil by ensuring that each strand occupies the same height position for the same distance as every other strand. Roebel transpositions represent a significant improvement over previous methods of transposition designed to reduce circulating current losses. Objective of transposition in the active part and transposition in the end region. Large generators usually tend to have a high power density and for which circulating currents in the armature winding can also be large. As the circulating current losses may lead to an overheating, so the corresponding loss must have to be estimated accurately in generator designing. During investigation, it has been concluded that high circulating current will be produced in the slot region if there is no transposition, especially external radial flux can produce by high circulating currents in strands close to the air gap. Therefore, in the active part in the slot region, the transposition is necessary. Otherwise, high circulating current will burn up the machine. Observation has been made. 1. 180-degree transposition in the active part reduces the circulating current. But circulating current can reach zero in case of a 360-degree transposition in the active part. Losses due to circulating current in the winding with transposition in the end region are less than the windings without transposition in the end region. In case of 180-degree transposition in the active part and 180-degree transposition in the end region, the circulating current loss is less than the case of 360-degree transposition in the active part and without transposition in the end region. Number 5, thus it will be cost effective to use a winding with 180-degree transposition in the active part together with transposition in the end region instead of winding with 360-degree transposition in the active part, that is slot region, without transposition in the end region. 6. Minimum circulating current almost to zero and losses have been achieved in case of 360-degree transposition in the slot region together with transposition in the end part. Number 7. Though leads to a somewhat lower losses, but for higher cost of assembly of the Roebel bars with 360-degree transposition as compared to the Roebel bars with 180-degree transposition could show an overall advantage of the case of 180-degree transposition in the active part together with transposition in the end region. Number 8. The strands bending is performed by programmable Roebel machine that allows to make 360-degree or 540-degree transposition at slot position as per requirement. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you.